In this video, we'll be looking at 5.4, solving compound inequalities. So our central question will be, how do I solve and graph sets of compound inequalities? So we'll start with the definition of an inequality. An inequality is two inequalities put together. Two inequalities put together. An intersection uses the word and this represents where both inequalities are true. So the best way to kind of think about this is using this what's called a Venn diagram with these circles. So if I have a set of numbers A and a set of numbers B, think of this as one inequality. Think of this as where x is less than 7, and then over here at B we'll put x is greater than 1. So where is it A and B? Where would A and B be true? Well, x would have to be between 1 and 7. So if 1 is less than x is less than 7, that's where we have both A and B being true. So this part right here where the two circles overlap, right there, is our intersection. A union is more of an or statement. So a union uses the word or. And this represents where either inequality is true. So if we have our A right here and our B right here saying, let's just make up an A. We'll say A would be less than -4 and B would be x is greater than 6. Well, we're just looking for numbers that satisfies either or. So even if I pick, say, -7, it satisfies A, but while it doesn't satisfy B, it satisfies as one of them, and that's all we need. In the intersection, we have to satisfy both. So for instance, 5, for our example, between 1 and 7, 5 is between 1 and 7, so it satisfies the intersection, but it would not satisfy, but if we picked a number like say 0, 0 would satisfy A, but it would not satisfy B. So the intersection has to satisfy both, whereas the union has to just satisfy one. So we could say, the way we'd write this is x is less than -4 or x is greater than 6. And in our intersection we have two ways of writing it. The one like we have in here 1 is less than x is less than 7, and then we could also say x is greater than 1 and x is less than 7. Okay, so let's look at these and graph them. For graphing purposes, anytime there's an and, it's really best to try to write it as that like one singular line inequality without any words, similar to this one right here. 1 is less than x is less than 7. So what I like to do is I like to um, write the inequalities so that they kind of have a flow to them where I have a number, my variable, and then these variables, since this inequality ends with that variable and this inequality begins with that variable, we can think of these variables as the x's is kind of like overlapping. So it would look like this. 5 is less than x. Now if I just overlap these, is less than 11. And when I'm graphing it, what we're graphing is the numbers that represent all the numbers between 5 and 11. So we'll still use our open dot, closed dot idea. So 0, 5, 11, and I'd have an open dot. And I want to represent all the numbers in between 5 and 11, so I would shade in between 5 and 11. On number 2, what we would do is, so that's our and statement. So when we have an or statement, it can be one or the other. So we'll do this. We'll just graph each one individually and see what happens. So I can have 0, 3, -3. I don't have my line underneath, so I'll use open dots. I'll do this one in green, like that. And we want to be less than -3. So we'll shade this way, including our arrow. And then, because we'll go on forever, I can have any number that's less than -3. -1 billion, for instance. And then at x equals 0, we want to be greater than 0, not including 0, and then every number that's greater than 0. So I can be 2, or I can be 47.3, any number greater than 0. And that's an or statement. So any number that satisfies one or the other will be fine. -7 satisfies this one, so the -7 will be a correct solution. Positive 112 satisfies x greater than 0, so that'd be a correct solution. The only numbers that are not correct solutions are between 0 and -3. Whereas on our first one, anything outside of 5 and 11 will be an incorrect solution, like -2, not going to fly. But say 7, since it's between 5 and 11, that would work. So go ahead and real quick try, pause right here and try number 3 and number 4 on your own. See if you can graph these. Okay, so hopefully you tried that out. Let's see if we can graph them. I'll draw my number line. 0, I have 8 and 15, so we'll just put 8 and 15. And it's an or statement, so I'm just going to graph both of them and not really worry about what happens. So we'll just graph them independently, and then we're done. So Q is less than 8. Put my open circle, no line underneath, and then it's less than, so I'll shade everything that is less than 8. And then Q is greater than 15, no line, so I will put my open circle, and then I want to represent everything that is greater than 15. And on number 4, we have B is between -1 and 10. So I'll put my 0, -1, 10. And we have less than or equal to, so I'm going to have closed dots at -1 and -10. And we would represent all the values in between -1 and 10. So I will shade in between, and that's where B is located, in between -1 and 10. Okay, let's go ahead and turn to the back side of this page. I'm going to skip 5 and 6 for now. We might come back to this a little bit later. And what I really want to show you is how to solve a compound inequalities when we're dealing with these. Okay, so let's do 7 and 8. So we'll just, 7 is going to be straightforward. It's just like solving two different inequalities. One problem, but two different inequalities. So we'll draw our line down the middle. We'll divide both sides by 3 on the first half. 3x is less than or equal to negative 6, so I'll divide both sides by 3. Dividing both sides by positive, so there is no sign flippage, and we get x is less than or equal to negative 2. We'll bring that or word down, and then we'll solve our other inequality. We'll subtract 7 from both sides, and I'll have 2x is greater than or equal to negative 2. Divide both sides by 2, and we get x is greater than or equal to negative 1. Dividing both sides by a positive, so my sign stays the same. And then we'll graph them. So I'll draw my number line. 0, negative 1, negative 2. Close dots at negative 2 and negative 1. X is less than negative 2, so I'm going to shade everything that is less than negative 2. And then x is greater than negative 1, so I'll shade all the numbers that represent being greater than negative 1. Like that. Okay, number 8. We will, okay, so for number 8, this is where, so our variable's in the middle right here. So now the idea in the past was whatever I do to one side, I do to the other. Now our thinking is whatever I do in the middle, I have to do to both sides. So it's kind of like we're doing two problems at once. So we'll draw two inequality signs, and or two lines to separate our problem, and then let's do this. So I'll follow my steps. The first number I want to get rid of is my plus 7. So I'll subtract 7 from everywhere. So if I subtract 7 from the middle, I have to subtract 7 from the left side and from the right side. So that gives me negative 12. My sign stays the same. Less than or equal to 3x is less than or equal to 3. Next, we divide by 3. So if I'm dividing the middle by 3, I have to divide everything by 3. I'm dividing everything by a positive. If this were a negative, negative 3, then I'd flip both signs. But I'm dividing them all by positive, so my sign will not change. And we get that. Forgot my line. There we go. So now we want to create a number line where x, our shaded region, is between negative 4 and 1. So let's draw our number line. Put 0, negative 4, 1. Close dots because of my line underneath. Negative 4 and 1. And x is between negative 4 and 1. So I want to shade all the values in between negative 4 and 1, like that. Okay, I want to show you number 9 because this one sometimes leads to some confusion. So if we already have this example, maybe we can avoid it. So the math's pretty straightforward, but a lot of times we have issues with understanding how this graph works. So if I subtract 1 from both sides, just doing that first, the first half of the problem, a plus 1 is less than 4. I get a is less than 3. Now if I do this, so I'll bring my or down, and now on this side, we'll add 1 to both sides, so we have a is greater than or equal to 4. Okay, so when we're graphing this, we have our a is less than 3, or a is greater than or equal to 4. So let's graph. Remember, when we're graphing an or statement, we just graph each one individually, and we'll live with the results. It's not in between two values. It's just kind of like two different graphs on the same number line. So let's go ahead and put our 0, then I'll put my 3 and my 4. Okay, so at 3, I have, I'm going to use two different colors for this one. At 3, I have a open circle, and it's everything less than 3. Like so. Actually, this one's pretty straightforward looking. And then at 4, it's a closed circle, and I want everything greater than 4. So I misspoke earlier. What I really wanted to point out is the situation that looks something like this. So this one, this is correct, but this isn't that weird. This is what we were kind of expecting. But let's say, let's see how this one. So let's say we have an OR statement where we do all our math and we get something that looks like this. A is greater than 2, or A is less than 5. So what would this graph look like? Well, we graph them both independently, and we'll see that if I do A is greater than 2, I have a open dot, and then I'm shading everything that's greater than 2. And then if I have A is less than 5, I'd have a open dot at 5, and I'm going to shade everything that's less than 5. So, the question is, what did I end up shading? What is my final answer? What can A be? Well, since it's an OR statement, A can be any number that is greater than 2 or any number that is less than 5. And when we look at the shading, I end up shading all the numbers. So what we could say is that when all this shading overlaps in OR statements, that my answer is really all real numbers, because any number is now possible. So I really wanted to show that piece off because this is kind of like a special case where you can get all real numbers when dealing with these compound inequalities. So that's it for compound inequalities. Thank you for watching this video, and I hope you have a great evening.